here in person in León, and well, our commitments didn't allow us to be there. So we are also in a general assembly meeting of one of our European projects. And I'd like to thank Raquel for giving us the opportunity to present some actual case studies of Pampas turbines already installed and operating in different sectors and different hydraulic infrastructure. So I wouldn't like to repeat much what has been already said in the during the final event, but I think that to start with, I will just briefly introduce the company. So we are EasyHydro. We started as a spin-off company of the Trinity College Dublin after a lot of years of research on the energy efficiency or of improving the energy efficiency of water networks. And after that, and from passing from the different stages of research in TRL1 to TRL9, we decided to pass to commercialize the cost-effective solutions for hydropower harvesting, especially at the scale of pico, micro, and mini hydropower scale. So we are focused on designing, supplying, and commissioning the solutions for recovering energy, hydropower energy from pressurized systems. And this basically brings three added values to customers. First of all, is generating 100% green electricity with almost, I'd say, known environmental impact, because this system are included or in the existing infrastructure. So we don't need to build any new pipe, any new reservoir, any new infrastructure to create or store the water. Then this allows to customer or water user to reduce their operating cost, and of course to reduce the carbon footprint. A typical scheme of a hydropower energy recovery system. Well, what is hydropower energy recovery system? So basically, it's just transform the excess pressure in water pipes, transform it into electricity instead of dissipating it in terms of noise, vibration, and heat. So typical scheme, and this is also always mandatory. It must be installed in parallel to a pre-existing, let's say, pressure drop system. It can be a pressure reducing valve, flow control valve, pressure sustaining valve, or a regulating valve at the inlet of a tank. Why should be installed always in parallel? So as water distribution networks, they always have to find a way to discharge the water that should pass through the pipe. So in case that there's a blackout, in case that some maintenance needs to be done or given to the turbine, the water will always find a path to keeps going down, keeps flowing. So basically, this brings us many opportunities in water distribution networks, like pressure management. With this pressure, well, with PET or with mini or micro hydro turbines, it allows us to reduce or to manage the pressure up to the minimum required pressure of the hydraulic systems. Of course, especially in Europe, where most of the water infrastructure they were built many years ago. So the pressure management also helps to reduce leaks. There's many research that directly correlate leaks with high pressure. So by means of managing those pressure, we could also reduce the leakage in our pipe infrastructure. Enhance the energy efficiency by means of producing or recovering some of the energy that is being dissipated or wasted, and self-consume that in the generation point, or sell it to the grid by means of export it. So that an overall view is that it helps to increase the energy efficiency of water user. And as I said before, reduce the operating cost by lower electricity bills, and reduce the carbon footprint by means of less energy imported from the grid that comes from a different share, and part of that share also include fossil fuels energy generation. We are mainly focused on pump-as turbine, but not just focused on that, and mainly because the pump-as turbine offers many advantages on the scale of mini and micro hydropower, and basically because they are an standardized technology that comes from a mass manufacture kind of industry, and basically that allows us to reduce the capex of the electromechanical equipment by means of 90 to 50% when compared to traditional turbines. The range of power is quite wide. We can go from units generating a few hundred watts up to over 1 megawatt just in a single unit. The maintenance is simplified. Is basically the same maintenance that we give to a pump. So that's also reduced the requirements in terms of experts to give the maintenance for custom made turbine, and also the current state of the art of pumps allows to adjust the materials of our PATs to different water qualities. We have solutions in bronze, in stainless steel AC 316 super duflex for desalination plants, or just cast iron that basically reduce the cost of the unit for clean water. I think that the industries where it can be applied, they have been already discussed, but just quite a quick overview. At the outfall of wastewater treatment plants, we can take advantage of the elevation difference and basically recover that energy before discharging the water into the river or into the creek. Pressurized systems that can be either in irrigation, in water distribution networks. So basically take the advantage of that excess pressure to generate electricity inlet of water treatment plants. And there's also an industry that is very strong in Asturias, for instance, that is mining. Mining is one of the main water user, but it's also a kind of a black box industry. So it's quite complicated to get information from this side. However, they offer quite a lot of opportunities to develop micro hydropower, mini hydropower system, and we'd like to show some of them in the next slide. So the hydropower potential several years ago, together with Inda, that I saw his presentation a few minutes ago, we developed some research about the mini micro hydropower potential across different countries in the Atlantic area of Europe, and the overall potential was about 500 gigawatt hour per year. That means 10% of the overall consumption of the water industry. However, we went a little bit farther, and we wanted to cross-validate this result that we obtained in the Atlantic area of Europe, and we collaborate with an NGO in Lebanon, and we saw that they identified also a huge hydropower potential in some of the sectors that we were assessing. But interestingly, they highlight that most of the potential that they identified, something like 20 megawatts, were coming from cooling system of a thermal power plant. Interestingly, we were already working on that sector, and we'd like to show some actual case studies that have been running already for years, and that we developed in the last 3-4 years. So this is somewhere near León. It's in a small town in Asturias. It's a water treatment plant providing water to several villages, and part of the water comes from a spring water. So before, it was not possible to discharge into this concrete break pressure tank because of the high pressure. But after collaborating with the operator, we designed this system to basically take advantage of the high elevation difference between the intake and the discharge point. And the system basically works for a flow more or less ranging between 55 and 125 liters per second, ahead of 30 to 65 meters of net head, and it varies depending on the water available at the spring. With this, we are generating something between 20 and 55 kilowatt of electric power. And interestingly, we are providing, when the PET is generating 40 or more kilowatt, we are giving 100% of the electricity consumed by the entire water treatment plant. So basically, during those days that they have 40 plus kilowatt of electricity of power generated by the PET, they are self-sufficient. They don't need to import any kilowatt hour from the national grid. With this, we are generating more or less 250 megawatt hours per year, and this helped the water treatment plant to avoid around 102 tons of CO2 equivalents per year. Another case, it's in an underground mine in the UK. This is a mine that at the moment is not operating, but they are draining they are making the drainage of the main shaft to start to resume operations of the mine. So as you can see, the mine is flooded. They are now dewatering the whole mine, and they need to treat the water before discharging into the river. So on the way back to the river, there's an elevation difference of 45-50 meters. And so we designed this system with the two PETs in parallel to adjust the hydropower generation to the flow regime of the water treatment plant. So at the moment, we are turbining between 75 and 300 liters per second, a net head of 45 meters. And well, it's grid connected. It just allows to, well, it helps to reduce the electricity consumption of the wastewater treatment plant. And yearly, we are generating 730 megawatts hour per year. You can see here the pipes where it was being installed, the discharge pipe from the water treatment plant. And here you can see the system installed underground, like 55 meters below the surface level, and with the two turbines installed in parallel and operating. In total, we are giving something between 80 and 88 kilowatt when both turbines are operating. We can also just run the small turbine. When it operates by itself, it generates like 27 to 30 kilowatts, and the big turbine can generate up to 65 kilowatt of electric power. Another case study is on all hydropower plants. So this is in Spain, in an old hydropower plant that use a water tank installed 67 meters up hills. But the case here is that the old Francis turbine that you can see on the right of the slide was stopped for the last 5 years. So basically, they were not generating any energy at this hydropower plant. So the operator just contact us to make a proposition and a design. And here is a 110 kilowatt PAT installed in parallel to the Francis turbine. It's been running already for 6 months, and it's generating something between 75 and 80 kilowatt of electric power, taking advantage of the 180 liters per second and 60 meters of net head. So yearly, we are generating 600 megawatt hour per year. And basically, we have bring back to life this whole hydropower plant, and basically start generating some megawatt hour after 5 years of dry seasons. Also, interestingly, there's the case of irrigation, which is also pretty strong in Spain. The case of irrigation, Cinda presented before the installation of the redown project, helps PETs can be a good solution to help farmers to bring electricity to remote places. In this case, this is in Pamplona. It's an installation that basically takes the water before entering into the irrigation pivot. And we had around 50 liters per second and 35 meters of net head that was being reduced by a PRV, a pressure reducing valve. So this is the installation itself is a very rustic one, but it's what the farmer wanted. So we have a small 2.2 kilowatt turbine directly feeding and storing the hydropower energy into batteries, and then feeding the irrigation pivot. So basically, with this, we allow to remove a diesel generator. So the benefit is that the farmer does not need to buy diesel anymore, and also the reduction of the emission associated to the irrigation basically were completely saved. This is in an underground mine. In some of the presentation before, I saw that the regions in terms of the range of head in terms of for single stage centrifugal PETs could go up to 100 meters. This case, for instance, with this multi-stage PET, we are taking advantage of anticipated by those three blue valves. So basically, the conditions at the inlet of the pressure reducing station were 27 bars. At the outlet, we had 5 bars, and what we proposed was this bypass system, and take advantage of the 22 bar to be transformed into electricity. So with a flow rate between 15 and 22 liters per second, and the net head of 220 meters, we were producing about 30 kilowatts. So this is in an underground mine in Ireland, something around 300 meters underground. Here you can see the actual picture of the installation, and this one's were the first installation of its kind worldwide. So yeah, it was a nice reference for us to be involved in the design, to supply all the equipment, and to commission such an interesting system. And for instance, one interesting thing that we have been exploring, and we have developed a few installations already, were aligned to the output of the report that the Lebanese NGO basically wrote a few years ago. So this is in a hydropower plant in Asturias, in the border between Asturias and Galicia. It's a 160 megawatt hydropower plant, so 4 Francis turbines in parallel, each with a nominal power of 40 megawatt. Here we have a net head varying between almost 100 meters and 150 meters, depending of the level at the reservoir. And basically, we take advantage of the water going into the cooling of the alternator and into the cooling of the bearings of the main turbine. So this system is quite interesting because the output power of the 40 megawatt turbine was capped because the alternator suffered of overheating in some of the points. So with our system, we basically allowed the hydro operator to regulate the flow going to the alternator and improve the cooling of the alternator itself. So after the commissioning, we made some tests with the main turbine 100% of its capacity. We basically improve the thermal efficiency of the system by more than 20%, and the turbine was running for 100% of its capacity for 8 hours in a row. So the good thing of this installation is that in 1 week of operation, the investment was already recovered, because imagine it's just a 20 kilowatt PET, but to this 21 kilowatt, we need to add 4 megawatts that the main turbine gain that basically before it was restricted. So overall, we can say that this system is of 4.02 megawatts, and it basically improved the overall performance of the hydropower plant. Well, and on the other hand, of the underground mine, this is a large flow, low head kind of system. Here you can see this is in a mineral processing plant in Italy. This is at the very last stage of the water treatment process. We have a clarifier of about 10 meters height and a flow that is being treated between 150 and 200 liters per second. To have an idea of the scale, here you have the height of the clarifier. On the left, you have the overflow pipe, which is at the end 1,000 pipe. So here is the before. The water was being discharged into a water pond. And here we have the after. So we took this small pipe to turbine the flow, and with the electricity that was being produced, that is around 10 kilowatt, we directly feed some recirculation pumps that we have nearby. So with this installation that is running 24/7, we are generating about 60 megawatts hour a year and avoiding almost 30 tons of CO2 equivalents. And with this, I finished the slides. I just wanted to present several cases in several industries of successful PET installation. So thanks so much for your attention. And if you have any questions, I would be keen to reply your question.
Bueno, ahora a continuación